please join me in welcoming Parash Rahman. He's a master's student here at the University of Alberta, and he's going to tell us about stochastic gradient descent in a non-stationary world.
Cool. All right, hi everyone. My name is Parash, as Abhishek introduced me. And yeah, I'll be talking about stochastic gradient descent and how the world changes and how those two things interact. So for some to motivate this idea of the changing world, well, I think that our AI has to have to deal with the changes in the world. All the data in the world is biased by a time and a place of where you collected it from. So we have to be able to, the AI has to be able to predict in such circumstances. For example, if you look at this white fluffy thing in the middle of the screen, it's like, what is that? Does anyone have any guesses for what that thing could be? A dog, that's a good guess. A waterfall, that's interesting. Air, yeah, it could be a bunch of things, right? We have like a little bit of information for the purposes of this example. In San Francisco, it could be a white dog, just like Fernando guessed. But these white fluffy dogs didn't exist maybe even 200 years ago. These are a recent invention. They're not natural. So in a place like Bangladesh, I didn't see many dogs that look like that. So in Bangladesh, it's more likely to be a man with an old man's beard, white beard. I've seen more of those there. And it depends on time and place. Are beards in or beards out? It just depends. And you have to be able to adapt to these changes. So the main point is that the AI will be wrong in some respects, in the future, and it could be more. It could be like an AI that designs things, like the designs will evolve, or an AI that sorts objects. The objects that it handles might change. So just generally, that's how I want to motivate change. So I just think we should be making our AIs for changing environments. And one problem formulation that captures this change is the online supervised prediction problem. In this problem, you get one sample at a time, and each sample has an input and a target. And the target is calculated by the environment with the target function, which takes in the input and gives it a target. So this target function could be human labeling data, or it can be learned as is done in reinforcement learning, where the target is the value of some input state. So however it's created, you get an input and a target, and this target function is hidden to the predictor, and so or the agent. So the agent / predictor attempts to predict the target given the input. So the predictor makes a prediction at a certain time, and hopefully the prediction is close to that target. And I bolded target function. The target function can change because, from my experiments, they will change. And this is just one type of change that you can experience in your data stream. So I'll be focusing on mapping from the input to output, input to the target, and I'll be focusing on how on its change. So what are some desiderata of online solutions? So I like the word desiderata. It just all it means is desired attributes or desirables of online solutions. So these are some desired attributes of the online solutions we should create. And this is from some surveys on online learning. So one is fixed memory. And then, so it shouldn't grow unbounded. So at least it should be bounded memory. Shouldn't grow unbounded, because what if the world keeps changing and changing and your agent keeps using more and more memory? That's not ideal. And computationally cheap and computationally fixed. Computationally cheap and fixed computation on each step. You don't want your agent to get slower in the future just because it has to do more computation, and you want it to be cheap so that it's fast. And then comes, it should be able to remember all important lessons of the past and learn new lessons in the future. So both of these make sense, but when you have a fixed memory, these become a trade-off. So being able to remember old lessons in the past might take up some space, and then to learn new things, you might have to adjust certain aspects of the memory, in the memory, and and if you remember everything in the past and then you run out of space and you can't learn new things, that's a problem. But if you learn everything that comes up, then you might overwrite a lot of important lessons of the past. So it depends on your environment. It's not very explicit how to do it in any given environment. I mean, sorry, not in any given environment, but like in many environments, it's not very clear how you would do this. So yeah, and these two things determine performance. And then finally, we shouldn't want our online solutions to have privileged information, in the sense that it shouldn't get information that's it wouldn't otherwise get when it's working in the world. For example, if the agent got information about when the world changed, like that's not really realistic, in the sense that sometimes the world changes due to factors outside of the observations of the agent, and so it can't really tell when the world changes. It can tell when it has high error, like it can be like wrong about a lot of predictions, but it can't really tell if the world really, like how much it has to adapt to that. It's not very, yeah. So to get in the mood of experiments, I wanted to first present a very simple experiment, simple gradient descent experiment, and to introduce gradient descent. In this experiment, we have one learnable weight, which is a scalar, and then we have a predictor which predicts that scalar. And why is that okay? It's because the target itself is also a scalar. So the target is sampled from a standard normal distribution, so mean 0, 1 variance. And the predictor will update its weight to try to predict that target. So the input of the predictor doesn't matter. It's 1. It will always be 1. So it's just irrelevant to this problem. But the weight is initialized to 0, and every 10 steps, the target is resampled. So the target can start at a number sampled from that distribution, but then it can go up, it can go down, it can go up and down. It can just change. It'll change every 10 steps. Okay. And then to update the weight, we're using a standard stochastic gradient descent update. Okay, so what does this graph show? So this graph, first the x-axis is the target number. So there'll be 19 target function changes for a total of 20 targets. So this graph for the 0th target will be listing a performance. What is the performance? It's the performance on the last step before the target changes. So the agent gets 10 steps to learn. On that 10th step, we measure that error, and that is what is plotted here. So it just so happens that, the targets come in sequence. So learning the first target, it does pretty well compared to later targets. The step size, when I changed it, can improve the error overall or make it worse. But this pattern of the first target being learned well compared to later targets shows up. Oh, keeps showing up. So why would that happen? Well, for this simple experiment, the target is 0-centered. So starting at 0 seems to be it is a good idea. And then but apparently learning from where you left off in learning from the previous target isn't as doesn't lead to as good of performance within that 10-step window. So this just the main thing I want you to get out of this is just that where you start with gradient descent matters, just because it might have to travel a longer distance in that sense. So then I want to, okay, so I'm going a little fast because I'm afraid of time, but are there any clarification questions or anything? So, okay, so now I'm going to make this experiment, transform this experiment into the multi-layer network setting. So now we're going to do stochastic gradient descent on a multi-layer network. This time, we're going to have a target network. And this target network is going to help us generate our data. So this target network has 7 inputs, binary inputs. It generates a random binary vector as the input, and then the input goes through the target network to get the output. Then the output and the input form a sample for the learning weight to learn from. So that is how we're going to be generating our data in this case with a target network. And the target network has LTU activations, which are linear threshold unit activations, and that just means the activation function is discrete. It'll be 0 and 1, as opposed to like continuous like sigmoid. And this is and the weights, all the weights, these weights, will be randomly initialized to -1 or 1 at the beginning, and then it will be reinitialized every 15,000 steps so that the target function changes. So you get 15,000 steps with one target function, and then it changes, and then you get a new target function. And it keeps doing that over subsequent target functions. And then for the learning network, we'll have also a multi-layer network, and they will have more hidden nodes than the target network, just to make it easier for it to learn. And the target network will always have 2 hidden nodes. The learning network, I will show you results for one with 15 hidden nodes and one with 40 hidden nodes. And yeah, the activations are sigmoid or tanh. Tanh work better for the learning network. And the learnable weights will be learned with SGD. Okay, so that's just the experiment design. Okay, and so what are the results? What happens when you use SGD on a multi-layer network and the target function keeps changing? Well, the error deteriorates. So okay, so what are these graphs saying? So the x-axis, let's look at the left graph. So the x-axis is the target function number. So it's there's the 0th target function to the 4,000th target function. And and the agent is exposed to each target function for 15,000 steps. So it has 15,000 data samples from that target function. And what the y-axis is measuring is the error on the last 1,000 steps of that 15,000 interval. Sorry, yeah, the average error on the last 1,000 steps on the 15,000 step interval. So right before the target function changes, we get the end error, like how well it learned that target function. And then that is what I plot, the end error for each target function. It's there's a lot of dots here because there's a lot of target functions, but it represents the end error after you had exposed to that target function for a decent amount of time. And yeah, so we find that as the target function keeps changing, the error deteriorates. And if you have, so on the right, there's more features, 40 features as opposed to 15 features for the learning network. And the error improved. So what I want to do, is I want to fill in this gap of error. And we do notice that in the first, when SGD is learning the first target function, it does pretty good. And I think we all know that. Like, we all know that SGD has been is a really good was a decent backprop in SGD and these algorithms. Really good at learning one target function. When they're kind of packed up against each other and they're next to each other and the target function changes, it doesn't get that same advantage as it got in the beginning. In the beginning, it's initialized in a very specific way. It's initialized with random weights, random small weights. That's pretty standard when people deal with multi-layer networks. So I'm thinking that maybe we can have that advantage spread out through, okay, sorry, I was looking at the comments. Maybe you can have that advantage spread out throughout the learning process, because as new target functions pop up, maybe you want to have a good starting position for stochastic gradient descent so that they can adapt to those new target functions better. So that is my, the hypothesis that I want to focus on now, and as I want to establish better in the future. So how do I do this? Well, I'll repurpose generate and test. So for generate and test, I'm using a simplified version just so that it's easier to explain it. In this algorithm, every 5,000 steps of learning, I'm going to randomly restart 5% of the hidden layer nodes, the input weights of the hidden layer nodes. So I'll take 5% of these guys and then randomly restart their input weights. And I choose the ones that have the lowest magnitude output weight. So that, like, the absolute value of their output weight is low. Why? So that their prediction, it doesn't affect the final prediction too much. So, and I'll restart those ones and see what happens. This is different from the original generating test proposed by Mahmoud and Sutton in 2013. And if you're not familiar with generative test, I would recommend reading that one.
So what exactly do you mean by restarting an input weight?
So when I say randomly restart, these weights in the beginning of all learning, the weights are initialized with some random distribution that's zero-centered. I'll use that same centered distribution to restart the weights of these input weights.
Just a quick extension to that question. So all the weights are independently chosen for every single connection?
Yes.
Okay, thanks.
Yeah. Okay, so how does that do? Does this restarting help with learning new target function, later target functions when using SGD? And it does. So these are the same green lines from before. So again, I think of time. So again, the x-axis is the target function number, the y-axis is the end error, the last 1,000 steps, and the target function changes every 15,000 steps. So we find that when I found that when using SGD and generate and test at the same time, the error for later target functions improved. So it was able to learn those later target functions better. And so, yeah, even in so on the left, there's only 15 features in the learning network. On the right is 40 features. So the 15 feature one with generate and test outperformed the 40 feature one with just only SGD. So there is an advantage of if you want in learning new things when you restart some nodes regularly. Why exactly that is the case is not fully established, in my opinion. So I personally think it's because you're giving a better start for gradient descent. Another possibility would be the SGD on its own can improve performance. GNT, generate and test can improve performance on its own. So if you just combine those two performance improvements, maybe you get better performance. I haven't tested GNT on its own alone yet to see if that's the possible reason why. But this is what I get for. So I got a question. It says, okay, do I ever go back to previous target functions and test? I do not. So I just randomly reinitialize the target function to get a new target function. I do not purposely go back to a previous target function that's been seen before. That would test something like, that would test, well, actually, I'm not sure what that would test. Yeah. I'm testing how well it learns new information, and a lot of the new information it has to learn conflicts with past information because the targets are changing. It conflicts with past information. So I wouldn't say this is a testable remembering even the one you provided. But anyways. So just in conclusion, so that we can get into the discussion portion. So the way I'm thinking that we have to consider the future, and that means to have our AI that adapt to the future, and that means it has to adapt to change. And I personally like the desiderata of online learning, fixed memory or bounded memory, cheap and fixed computation, remember important lessons of the past, learn new lessons in the future, and don't use special information from the environment. And to me, the remembering versus learning trade-off is more explicit in an algorithm like generate and test, where you explicitly forget certain weights depending on how useful they are. Then in SGD, I think in SGD there are probably ways of establishing what it learns and what it remembers. It's not too bad when you look at the actual updates itself. It's just I didn't really hear about it. And yeah, so my hypothesis is that SGD can be improved by lowering the error gap so that it doesn't have to travel as far. And on average, it doesn't have to travel as far. And in the future, hopefully, generate and test algorithms can generate history-relevant features. So rather than just a random feature, it can generate features that either allow SGD to learn better or just generates features that are just useful in their own right, and that you can basically close that error gap to the point where it's not existent. But that would be like really far. Well, not really far, it'd just be different. But yeah, I was just focusing on how to improve SU, just to bring it into the limelight. So yeah, and that is my talk. Any questions? Oh, comments, of course.
Yeah, so I was wondering that that the 5% number that you're talking about, that you randomly restart 5% of the features at every, let's say, 5,000 steps or something. So I suppose this number, like the performance would vary quite a bit depending on, how many nodes that you have and how many features you decide to reset and at what point. So have you tried any, like for example, with the percentage, if you think if you increase it from 5% to, let's say, 50 or all the way 80 or something like that, then you would see performance deteriorating at some point. Like it would probably go up and then maybe come down. So have you tried something like that? And maybe do you have any idea how you would set that number in general?
So I haven't, so when I got this number 5,000 and 5%, these are hyperparameters. I tested like 2 hyperparameter settings, and that was related to the number of steps, so 5,000 and 10,000. It would be a good idea to see how the amount you restart affects things, just to make sure it's like working well, and to see how sensitive it is to these parameters. Like I just wanted it to be infrequent. From my past experience, I found that an infrequent generating test worked well, so that's why I did it infrequently. But I will be converting back to the original generating test, which changes a very low percent of the nodes every step. So it's just a different way of saying the same similar thing, that 5,000 steps. It will just be, rather than 5,000 steps, it will just be a low percentage chance of changing some of the nodes. Just so that I don't have to choose these numbers that are very problem dependent, like 5,000. It's much more connected than the percent on every step, even though both, it's a similar effect anyways. Just less explicit.
Cool. So was there a particular reason why you chose to do changing this at like after n steps rather than how it was originally proposed?
Oh, just to make it easier to explain. Okay. Like it's easy to understand. Like otherwise I would have to explain some other details.
Okay, cool.
Hey Parash, so I have a question. I think so. So I think there's two problems going on here, but the one you're talking about right now, which is like resetting these weights. So I'm thinking that like there's this common folklore idea that if you reset the weights such that they're orthogonal, so that the first layer weights represent orthogonal vectors, then you get sort of better learning performance, right? Because you're kind of you're extracting sort of the information in different directions from your input, right? And so there's this common idea that when you initialize the weights, you generate an orthogonal matrix. And if you just randomly generate a matrix with independent normal entries, then that's going to be pretty close to orthogonal, right? So one possibility for what you're seeing is that you initialize the weights to be orthogonal, but then over the course of learning, they become less and less orthogonal, right? So it becomes harder to learn sort of new signals. And then by sort of reinitializing the weights periodically, you're maintaining orthogonality, right? And maybe one way to test that would be to actually find out like the rank of the weights, right? If you, as you were doing these experiments, if you plotted this quantity, right, which is like how orthogonal are the weights in the first layer, that would tell you whether this is what's actually happening, right? Whether the orthogonality collapse is what is stopping learning in the future sessions, and whether and then there might be other ways of maintaining orthogonality, right? So rather than refreshing the weights every once in a while, you might be able to have some sort of regularizer that tries to make the weights remain orthogonal. So that's one thing. The other thing is, the other problem is kind of apparent from your first example with just the scalars, which is that if you have a target function that's changing, let's say every 10 steps, right? and you know that it's changing roughly every 10 steps, then you really want your learning rate to be so high that you try to like do as well as you can in 10 steps, right? Like you do not want such a small learning rate that your gradient descent is kind of, by the time it even gets close to the target has shifted again, right? So in this sense, like let's say there's no noise, you're just doing gradient descent, but the target is shifting. And if you know roughly how often the target is shifting, then you should be setting your learning rate high enough that the gradient descent has a chance of converging before the target shifts, right? So that's like a learning rate tuning problem, right? And that just kind of happens in these sorts of shifting settings, right? If you know you're shifting very quickly, then your gradient descent your learning rate has to be high enough that you will actually track that, right? So yeah, so the reason I'm saying that is because if you sort of experiment with what a good learning rate is in that scalar setting, then that might entangle these two sources of issues that you're having, like the failure to track versus the sort of the collapse of the features. So yeah, just a couple of comments.
Sorry, I'm getting a bunch of questions. So, sorry, you're saying that changing the learning rate, the step size in this setting that I'm showing on the computer would stop this problem?
Yeah. So imagine that, let's say that you had very short episodes, right? Maybe you're running gradient descent with a fixed target function, and you only had 10 steps to learn. Now, then you would set a fairly high learning rate, right? Because it doesn't matter that you converge in 100 steps, you have to converge in 10 steps.
So it would, okay. I mean, so I guess if you set the learning rate to 1, it would converge in 1 step, right?
Well, assuming that there is no noise. And
I don't have any noise.
Yeah, you don't have any noise. So it's not stochastic gradient descent. And if the loss function is quadratic, then that's still not the best thing.
So the thing I found that when I increased the step size, the overall error would improve for all the points. It's just that this one would just be slightly less still. It would still, the first one would still be less in terms of error. So the difference between targets is constant. However, the difference between where you start and the target at the beginning of when the target is introduced is lower for the first one than later ones. So
is that just because you initialize the weight to be 0?
Exactly. Yeah.
With 0 centered distribution, so it's just like twice as big or something. But like, is that really interesting? Like, do you really care that the initialization, like, if you initialize to be a normal 0, 1
so
normal,
in this case, it's like a single weight. Like, you can't really, like, it's like doesn't matter in this. Yeah, it's like a trivial problem. But I guess the thing I'm questioning is what happens when you have like way more weights and when you have like when you're shaping your features and you don't know which way, if they're going to go up or down, and the world also changes. So it'll just be like, does this accumulate? Does this add up? Does this effect add up of like starting at the beginning, like starting with a good initialization? It works really well compared to starting learning after learning a previous target function.
Right. So you're saying that the main feature that this experiment is capturing is that somehow the initialization is better for learning than the weights later on in the process, right? Yeah. And here it happens to be trivial. The initialization is just closer to 0 than everything else. But then in the other situation with the neural network, then you might have some non-trivial interactions, right, between initialization and learning, and that's what we were talking about before with orthogonality and so on.
So yeah, in between the two experiments, I want to do even simpler, where the node, it's a single node, and maybe even a fixed output weight for both the target and the learning, just to see how whether this phenomena happens across all views. So yeah, I didn't have that ready in time for this presentation, but yeah, that's definitely something I want to check.
I guess my main point was simply that you have to set the learning rates based on how quickly you expect the target.
Yeah, definitely. So for the multi-layer network one, I definitely, so I did a hyperparameter search for the step size parameter. And I even did I had 2 step sizes for each layer. One for the input layer and one for the output layer. And I also did a search for good initializations for SGD. So the variance of how of the weight initialization of the representation layer. So yeah, I did. So I did it for. I optimized it for learning a single target function.
Okay.
My newer experiments will optimize it for a few target functions, just to make sure just to give it a chance. But I did see the same thing. I didn't. These are kind of old slides, sorry, but yeah.
Right. Okay, thanks.
Yeah. And also on your comment of orthogonality and like the other factors, yes, I think there are a lot of things that like there are other explanatory factors that could like that are correlated with this phenomenon. I'm trying to figure out like how to separate these things. So, but thanks for that possibility.
Now, there's a couple of questions in the chat that you might want to check out.
Do you check if, okay, so this question is, do you check if restarted nodes contribute a lot to the predicting a new target function? No, I didn't check that. That sounds, checking if they contribute a lot if you restart. Actually, that would be interesting to see how, say you were learning one target function and then a new target function appeared, which weights were more useful? Was it the newly restarted weights, or was it the old weights that weren't restarted? And how old were they when they were contributed greatly? I might do that. I'm not sure if I will have time for that, but yeah, that sounds. Yeah, that would actually help. And maybe that might help answer the question of whether restarting helps SGD, just because you're in a good starting position, or for some reason SGD clamps onto it. But I haven't done it yet.
So I guess I have another sort of comment based on what you've been talking about. So if you want to study what it is about neural networks that makes them fast to adapt to something, right? That is basically a question of initialization, right? The neural network is in some state. I give it some signal, and then I train it for a few steps. And how quickly does it converge to that signal, right? That is like ultimately the basic question being asked. It doesn't really matter that the initialization, like the target is changing, all of that, right? Like it's captured under here, right? So I wonder, because I do know that there is a fair bit of literature about like how to initialize neural network weights. Yeah.
Well, I mean, yeah, I mean, so in this scenario where it's like changing, it might be like ideal to like totally restart the network when you experience a big change. Then you learn that new target function really fast. But
oh yeah, sorry. I didn't imply that was a good algorithm, but I meant to imply that question of how to initialize a neural network such that it converges is a simpler version of the question you are asking, but that captures some of the same problems, right? Because if you know that a neural network with a certain set of weights is going to converge faster, then you can ask the question of how do I maintain that set of weights even in the middle of my training, or maintain that property of the weights even in the middle of my training, such that if the target changes, then I can adapt to it quickly, right?
I see. already.
And Rupam had a question in the chat about
Oh,
did you tune
yeah.
the
So,
size
oh,
to the
okay.
annual?
I mean, I guess I answered it when answering someone else's question. Yeah, I did tune the SGD parameters well enough that the first target function it learns is really good in terms of performance. Yeah, hyperparameters themselves are kind of special information about the environment in a way, privileged information, because they kind of you're given like this oracle that tells you which hyperparameters you should use. So it's an ideal to not have privileged information about the environment, but selecting the proper hyperparameters for SGD or even generating tests, it just seems it just wasn't perfectly clear about how to, like, which is the best way to do it, especially for an environment, a world where things keep changing.
Yeah, can I add something to that?
Yep.
So in general, this question of like avoiding privileged information, adapting to a wide range of environments, it's a very interesting and good one. For this case, when you have full information, that is, you have targets, the online learning literature tells us that there should be almost no price for adapting to the rate of the change of the environment. And there are very simple ideas to achieve this. It's basically keeping a host of models. Like you oversize your neural network because you are preparing for a change. So you can kind of do the same. Like you would keep a host of models. Each of them is, like time to time, maybe reinitialized, using different learning rates, set up in a very principled way. And you would simultaneously measure in parallel how well they are doing. And you might think that, okay, like you would just listen to the one that is doing the best, but it's slightly better if you're mixing the predictions. And there are good ways of mixing the predictions of these networks. And if you do all this well, then the theory goes that this is a very, very good way of adapting to a wide range of environments. Yeah, which is kind of interesting. So it's not as homogeneous as just having one neural network and one SGD rule and doing this, but it's a little bit less homogeneous, but at the same time, it has very, very appealing theoretical properties. So I was wondering whether you have looked into this literature, know about it,
Yeah.
interested in it.
So I did look into it early when I was looking into online learning. It's one of the first things that pop up. It's just having multiple neural networks. They're trained in different ways. I was still curious about what if you just had one neural network, as you mentioned, that there are some parallels to what I'm doing in one neural network to what you just described as the multiple neural network setting.
Yeah.
Just because it's easier to run really long experiments with one neural network. So I can run because some of these effects don't happen until like a long time if you have a very complicated environment. But also it's kind of, in my opinion, hiding what SGD is doing within a single neural network when you're learning multiple neural networks.
Maybe that's not a bad thing.
I do think that there are good things about being able to look at taking into account the structure of your function when using SGD, because
I
then you can
think
see.
that it would be curious to just have one neural network that is able to compete with this idea that I described. Yet I think that like that's the baseline that you should be comparing with, right? Like we know how to solve this problem. If you are claiming that you have some way of addressing the same problem, maybe you should compare with solutions that have good properties.
Mm.
I mean, it's
Yeah,
it's not necessarily a race, but it's still, you know, like I guess homogeneity of the architecture has some advantages, but if these advantages are overshadowed by limitations in performance, then maybe a practitioner would want to know that, right?
Yeah. Yeah. There's also other online learning algorithms that do focus on a single neural network. Like there's one where rather than replacing nodes, you add nodes and it grows.
Yeah. But that's
like
why
stuff
it's
like
one
that.
of your principles.
Yeah. I guess what I see what you're saying. So the one thing appealing about the architecture you're talking about with multiple neural networks was that it actually did follow a lot of the principles, and I was surprised. I was like, how is that a thing that it can work well? It'll be interesting to
I
test
think
the
that
limits of it well.
in order to get the best theoretical results, you would still want to slowly add new modules, but it would be a logarithmic growth so that you can ignore it. Like, and then, okay, you will have some limitations because of that, but it will be a very tough comparator to compete with that. And there are others like the forget-me-not from the DeepMind folks and whatnot. I'm not like super familiar with the details of that, but like this problem has been around.
Yeah. Oh yeah. And there's ones that operate on the weights themselves specifically.
Right. So that's more similar to what you're doing. I'm like it's like superficially similar, but yeah.
Yeah.
It's actually quite different still. It kind of monitors how fast the weights are changing, and based on that, it decides whether the weight is should be frozen or not. But yeah, it's a good problem.
Yeah, thanks for the comments.
No worries.
All right.
I just wanted to say, like, based on what you're saying about multiple neural networks, so one of the advantages of neural networks is that they're fairly compositional, right? So I wouldn't be surprised if you can write an algorithm, at least some kinds of algorithms with multiple neural networks, as one larger neural network that has a particular structure, right? So maybe you do like some special gradient descent on some particular layer of network, but otherwise it's like a totally normal thing, right? So I guess neural networks are a language for expressing problems, right? So you shouldn't limit like expressible problems, right? Multiple neural networks are not that different from one, right?
Yeah, that makes sense. Like, I mean, I see where you're getting at, like the architecture.
Yeah, like as a simple example, imagine that you have multiple neural networks and you're doing sort of prediction with expert advice, where you're thinking of each neural network as an expert, right? The algorithm for prediction with expert advice happens to also be a gradient descent, but with mirror descent with some regularizer, weird regularizer, right? So if it's just like 2 layers of gradient descent, then you can always collapse that into one, like a big network with gradient descent, as long as you're using the correct geometry or whatever for the gradients, right? So in some sense, the result of such an algorithm design would be saying that a particular type of neural network structure is better at dealing with these sorts of problems, right? So it's like first you come up with architecture and then you translate it into neural network form, right? Because that's just a language for expressing certain kinds of computations, right? instead of saying that somebody has given me a neural network architecture and then how do I hack the optimization algorithm to make it work, right?
So I see a question in the chat. It's asking, how does it compare to meta learning approaches like MAML, which learn a k-shot optimized prior over the task distribution and use that as a starting point for adaptation? So this one sounds like you're optimizing over a specific amount of tasks, so you kind of have to know the structure of the changes. Even though the changes in my experiments are very regular, except for like the hyperparameters, I did try avoiding like the agent, like SGD and GNT are pretty like agnostic to like what's actually like the higher structure of the world. In my opinion, the more relevant meta learning ones would be the online meta learning algorithms, such as IDBID or SMD, as it's called when you apply to nonlinear settings. And I forgot what other one I tried. And other optimizers, just try other optimizers that are supposed to do something special to account for changes and learn better, such as Atom or RMS Prop. Oh, no, Atom includes. But yeah, so I did try other things like that, and I got this similar trend. I'm not really sure which ones are the best in terms of meta learning. But yeah, I'm more focused on the online learning algorithms more so than offline ones. Because I don't think it's reasonable to expect that you can gather enough data that you can somehow learn all these different changes, like especially for something that works in really fast real time. Like that's just a lot of data.
All right. If there are no more questions, let's all thank Parash for the interesting talk.
All right. Yeah, that's it. So see y'all.